All right, Mr. True, back again. We're going to finish our introduction to probabilities and start talking about the two general rules of probabilities. You know how we say like or means add, but that's only if the events are disjoint. So probability of A or B equals a probability of A plus a probability of B if it is impossible for those two events to occur together. Well, if it is possible for them to occur together, we need the general addition rule. And that says that if the probability of A or B equals the probability of A plus B, but if I just do A plus B and those events have a chance of occurring at the same time, that overlapped area is going to get counted twice. So we're going to have to do minus the probability of A and B occurring together. So that overlapped area, like I just said, it's counted twice. So you must subtract that area once, to cancel out the double count. An event diagram, which is about what I'm about to set up for you, as shown on the left, but not yet. You would not count this area twice, so the diagram simplifies the mathematics. And indeed, we're going to be learning these two general probability rules. These general probability rules will be given to you on your AP Statistics exam. So you don't need to memorize them, but you do have to know how to read them and know how they work. But even the textbook will tell you that we do a lot of calculations with Venn diagrams and tree diagrams, like I showed you how to do on the previous video, introducing the two-part video, or actually three-part video of introducing probabilities. There's an example of how to do a tree diagram, and that's when you want to find the probability of a sequence of events. Well, I got this very generic label up here. Maybe A is somebody drinking soda, B is somebody who drinks tea, and then here's the probability that they both drink the same drink, or whatever. I don't have the room to write up a word problem, or the time, or the space to write those out. So just kind of like a generic setting. Probability of A has 40% of occurring, probability B has a 30% occurring, and probability of A and B has a 12% chance of occurring. Now, again, I did not write out an entire word problem for us to read and try and break down. That's what you want to do when when you read the examples in your textbook and you talk to your teacher in your class. But with this, they're very plainly laid out. We can see we're just going to do 0.4 plus 0.3 minus the overlapped area of 0.12. But let me show you how you would set up a Venn diagram from this notation here. To set up a Venn diagram, you draw a rectangle, and that rectangle represents the entire sample space. Okay, so the area or the probability inside this square is going to be 1. Now, it's not a density curve, but it's kind of like that, where this is the entire sample space. Now, inside the sample space, we have a couple of events of A being 40%, but I'm just going to put a circle and say, well, I'm going to call this circle A, and there is a possibility these events occur at the same time, so I'm going to leave an overlap. And within that overlap, that's going to represent the probability that both of those events occurring. And so I'm going to put a B over here. Now, here's the Venn diagram. We have event A, event B. We have an overlapped area, which is going to be A and B occurring together. And then we have some empty space around those circles because maybe A and B don't even occur at all. If it's a survey and it's about somebody drinking Coke or tea, maybe somebody doesn't drink either one of those. Well, that probability would be found in the outside area of this Venn diagram. Now, when you set up a Venn diagram to try and help you answer probability questions, and by the way, this is not a sequence of events. This may be just, as a survey, asking somebody one question, and then you can get multiple responses from that one question. A series or a sequence of events or trials, that would be solved or worked out through, again, the tree diagram like I talked about in the Intro to Probabilities video. So when you set up a Venn diagram, you want to do the overlapped area first. So the probability that A and B occur together is 12%, so 0.12. And that's a probability they both occur together. Now, the circle for A, the probability of A occurring, period, regardless of B occurring or not, the entire circle has to represent 40%. Now, this is why you want to do the overlapped area first, because that entire circle must add up to be 0.4. Well, this entire circle has 0.12 already represented. So 40 minus 10 is 30, minus another 2% is 28. So this area of the circle has the probability of 0.28. This circle, and I'll explain how you label that in a second. This circle, this entire event B, well, the entire probability of B occurring is 30%. Well, we already have 12% counted in the overlapped area. So this entire circle, by this notation, has to add up to 0.3. So 0.12 means that this outside area is 0.18. And so that those two add up to 30%. Now, let's see what's left. We got 28%, and 12 is 28, 38, 40, and now we're up to 50, and now we're up to 58% total. Well, an entire sample space must add up to the probability of 1. And now that I'm talking, I just forgot the number. But whatever is remaining is going to go on the outside of those circles and be within this rectangle. The Venn diagram is defined, the borders are defined by the rectangle. That's not me just highlighting these two circles. So 28, 38, 40, 50, 58. So outside those circles, 1 minus 0.58 is 0.42. Right? Let me just double check that. 28, 38, 40, 50, 58, 60, and 1. Good. So now we have probabilities all over this Venn diagram, and I can answer a lot of questions. Now, I can make off a list of notations and questions here, which I may still do, but I want to show you how to highlight or how to label this Venn diagram. Inside this part of the circle, event A is occurring, but not B. So this would be the probability of A and not B. The uppercase C is representing the complement. That again, the complementary events is either event occurs or it doesn't occur. So B with an exponent of C is the complement to B, or B not occurring. We're not inside the circle. We're in circle A, and we're not in circle B. This, as already noted, the overlapped area is the probability of A and B. Over in this circle, the 18%, probability, that's B occurring and A not. So that notation will be the probability of A and B. Whoops, I forgot the complement on A. This is the probability of not A and B. So what's the probability of B occurring without A occurring? 18%. What's the probability of A occurring and not B occurring? 28%. What's the probability of neither one of them occurring? Well, that's 42%. So from setting up this Venn diagram, I can answer a lot more questions than just what's the probability of A or B. And by the way, I didn't even answer that question yet. So what is the probability of A or B? Well, this would say, without the Venn diagram, 0.4 plus 0.3 minus 0.12, or with the Venn diagram set up, we just count all the areas that are either in A or B. Well, that's 0.28 plus, and I'm just working my way across the Venn diagram, 0.12 plus 0.18. And that comes out to 28, I know I just did this a second ago, but 28, 30, 40, 58%. So the probability of A or B occurring is 0.58, but with the Venn diagram, I can find the probability that neither one occur, the probability that A occurs and not B, or the probability of not A and B occurring. So see, these Venn diagrams not only simplify the mathematics, they also make answering other probability questions from the same setting much, much quicker. Now, before I move on to the next topic, are A and B independent of each other? Well, one of your probability rules that you learned in the previous video, the intro to statistics, or the intro to probability videos, excuse me, get my words all mixed up, says the probability of A and B equals the probability of A times the probability of B if they are independent. Well, they gave us the probability of A, they gave us the probability of B, and they gave us the probability that they both occur and that's 0.12. Well, if I can take A and B and multiply them, well, that would be 0.4 times 0.3, and if I get the same answer as I'm told their probability of them occurring together at the same time, well, if that formula does actually come out to work, validates the given numbers, then those are indeed independent. If we had been told that the chance of them occurring together was maybe 20%, then 20% would not equal 12%, and our conclusion would be that they were not independent. So again, we do talk about independent trials, and in this setting, we were talking about independent outcomes. All right, second page. Woo! I'm sure this is going to be a two-part video, because that took a while. Alrighty then. I've got just a few minutes and we'll start part 2 in a second. Now we're going to revisit an earlier video, an earlier topic about analyzing the probabilities between categorical variables in a two-way table, and we talked about finding row and column percent. So row and column percents are a form of, or they are, conditional probabilities, but we did not actually introduce the proper statistical notation of what a conditional probability looks like. We just knew when to find a row and column percent. So we're going to revisit that and then move on to another screen and tie in the actual proper statistics notation that go along with those conditional probabilities. Well, conditional probabilities, this goes back, I just said that. So here we got here we have a two-way table. I got a lot of knowledge, but all the words are coming out wrong in this video, it seems like. We have a two-way table, and we're comparing the grade earned on for a student and what classes they're generally taking. Well, okay, so we got grades of A, B, C, or just below. Of course, nobody in my class is doing below a C. And we got 3 topic levels of math, English, and social studies. So between these grade distributions and these 3 main subjects, we have a total of 2,500 students. Well, from this two-way table, let's answer some questions. What percent of the students have A's in general? No condition given, just what percent have A's? Well, that's 541 divided by 2,500. Well, what percent of math students earned A's? Well, now I don't want to even have the student be considered unless they're specifically a math student. So where is the variable of being a math student? On the side. So that means that what percent of math students earned an A, I only care about the students who are in math classes. That means that we're setting up a row percent. So it's going to be 112, those math students that got an A, divided by all the math students of 800. That's a row percent. What if I turn the question around and I say what percent of students with A's are math students? So in this sentence, the condition is you're a math student. In this sentence, the condition is you are an A student. Well, A students is the top of the column. So instead of doing a row percent for math being a condition, we're doing a column percent where the grade is the condition. And we have 112 divided by 541. And my last example is what percent earned an A and was a math student. You see the change in language there? There's no condition given. Just what percent of all the students got an A and were in math. That's 112 out of 2,500. I'm Mr. True. Part 1 is done. Part 2 coming up. Woo! Woo! All right. Part 2 of my introduction to the general probability rules. We just got done talking about the general addition rule. We just got done talking about how this topic, the general multiplication rule, ties in with a lesson that we've already done, which is finding row and column percents on a two-way table. And that's not the only setting where you have the general multiplication rule being required, but it's a really good tie to a previous topic. For the general multiplication rule, A and B do not need to be independent. The notation is the probability of A and B is equal to the probability of A times the probability of B, given that A has already occurred. This type of conditional probability was again addressed in my example of the previous three-part video, Introduction to Probabilities, where I talked about the performance of students in my class as far as their grades were concerned as semester averages, and then used that success or performance to base their probability on whether or not they passed the AP exam. Those are not independent events. They're actually very dependent. So this notation would have been appropriate for that type of question. Now let's put it in word symbols, and then I'll put it into the example I just said. Probability of A and B equals the probability of A times the probability of B, given that A has already occurred. So in my example of class performance and the exam performance, what's the probability that you do well and you pass the exam? Well, that was the probability you did well times the probability you passed the exam, given that you did well. Or, what's the probability that you did poorly and passed the exam? Well, that would be the probability of you doing poorly times the probability of you passing the exam, given that you did poorly. And the tree diagram I did for that example looks something like this, where it was, how did you do in the class? And then, how did you do on the test? And if you would like to watch that Intro to Probability lesson, please do so, because I'm trying to help you guys out, and I got more to talk about this two-way table and not about a tree diagram that I've already set up. But if you do have a sequence of events that you would like to find the probability of, you do use tree diagrams to solve those probabilities, or to help you solve those probabilities. So of course your performance on the class will determine your success in the test, and that dependent probability set up in the tree diagram. This line, as you just heard me say, is read the probability of B given that A has already occurred. The conditional probability, this part of the formula is the conditional part. How did you do on the exam given you did well in the class? That conditional probability can also be checked, is it really conditional? It may be that it's independent. If you have enough information, you can check, is the probability of B equal to the probability of B given that A has occurred? If the probability of a student passing the exam was the same as the probability that student passing the exam given that they did well in my class or poorly in my class, then that would show that the grade or the passing rate of the exam was independent of the success in my class. So again, if the probability of B, just B occurring alone, is the same as the probability of B given A has already occurred, if those two are the same, then A occurring had no effect on B, and thus those are independent events. This notation, this formula, one version of this formula is given to you on the AP exam. This is in my book. I think this is the one that's on the exam. I guess I could look. Let's see here. Why, yes, it is. So if we take the formula as it's designed in my book, and I divide both sides by the probability of A, and I get the probability of B, given that A has occurred alone, you'll see this version of the formula. Now, I actually do prefer this version, so I'm glad to give it to you on the AP exam. And one thing to note, that the given that part, the condition, is the denominator. So the condition and the denominator are always going to be the same. Now, you may not have realized it with the first or the end of that last video, part one of this video, but when we did the conditional probabilities out of that two-way table, we were actually adhering to these formulas, and I would like to try and show that to you in the last few minutes of this video. No. Squeeze that in there. Okay. I hope this type's not too small for you to see now. Okay, hopefully you can read this. We have this two-way table, and I said, in this example, what probability of math students earned an A? Well, the condition is being a math student. So we have the probability of A, given that you're in math, and it came out to be 112 divided by 800. Well, let me try and show you how that ties in with this conditional probability. The probability of A given B equals, the probability of B given A equals the probability or the number of both. Now, of course, this isn't a probability, but you can see that it's something about A and B occurring at the same time. Well, where did the 112 come from? That was the students getting an A and getting, or being a math student. So that 112, well, it's not a probability. It has something to do with A and B or A and math occurring at the same time. Whereas the denominator, the probability of B given that A has occurred equals the probability of both divided by the probability of A. So the condition has a lot to do, everything to do, with the denominator when you set up a conditional probability. Well, why do we divide by 800 and not 2,500? Because we're talking about math students, and there are 800 math students. So the 112 divided by 800 is very, very similar and almost exactly the same as the conditional probability formula. I'm not saying exactly the same because these are counts and not probabilities, but I want to show you the tie-in with something you've already learned with fancy notation that you're now seeing in chapter whatever it is in your book. In mine, it's chapter 6. What percent of students with an A are math students? Well, now the condition is A. The condition is you have that A grade. So the probability of being a math student, given that you're earned an A, is again 112, because again, we need that number where both of those variables are, A and math. That's 112. Or A and B, right? And then the denominator is 541 because, of course, the condition now is not you being a math student, but you earning an A in the class. So the denominator is 541. That A, again, was at the top of the column, and that is the condition. That is the total number of A's that we got. So again, see, your condition is what sets up the denominator of your conditional probability formula. I'm Mr. True. Bam! Go do your homework.